today is this is going to be the video that kind of hopefully will wrap up instruments for us here before we get into chapter 9. So we're going to pick it up where we left off here, and this is going to be on the turn coordinator. So as we look at the turn coordinator, remember that the turn coordinator gives us a couple different types of information. It tells us, are our wings, let me change this, are our wings level across here? That's a little big. Let's change that a little bit. Let's kind of make that a little smaller. Let's go with, do I have something else here? I can't tell what this one is. That's a little fine. Let's try this one. How's that? Is that a little, well, that's about the same. Wow, I don't know what happened to all my markers. Crazy. I can't keep anything nice here in this house. So if you have your aircraft and you notice that the little miniature airplane inside your turn coordinator, if you have the wings that are touching both sides of those marks, you know that your wings are level. And that's pretty helpful. And you think, well, duh, I should be able to tell if my wings are level. Well, sometimes you can, sometimes you can't. If you are in the soup, you may not be able to tell. Then you can also look here at this particular illustration, and we see that we have our right wing down here to this particular little tick mark. Well, what does this little tick mark tell us? That little tick mark tells us this right there. You see that information there that says 2 minutes. What that does is this. When you are attempting to turn an airplane, in the instrument world, we want to make sure that we're conducting our turns in what we call a standard rate turn. So what that means is we want to turn the airplane approximately 3 degrees per second. So let's do a little math here, shall we? I want you to write 360, because that's how many degrees there are in a circle, correct? And I want you to divide that by 3. What do you get? 360 divided by 3. Go ahead. Those of you that have just now said 120, that is correct. How many seconds are there in 2 minutes? Well, that's right, 120. So what that means is this. When you have the aircraft in a coordinated turn, banked with the wing banked on that line, you are turning at a standard rate of approximately 3 degrees per second, which will give you one complete turn in 2 minutes. Why is that important? In the instrument world, if the FAA tells you, November 141 Hotel Lima, give me a right standard rate turn for spacing, please. What does the air traffic controller need? He needs to buy 2 minutes. By turning standard rate 360 degrees in a right turn, it just bought him 2 minutes for spacing. There may be somebody else that's coming in on an approach. We need to get them out of your way. Need to kind of sort some things out on the ground, whatever that happens to be in order to get you down. That may be one of the reasons why. So we practice doing turns at standard rate. In this particular aircraft, this is how we do it. We do it using our turn coordinator here, giving us that information here, telling us about how we do standard rate turns. Okay, so that's part of it. When we look here and we look at our G1000, we actually have something else. And again, I can't do this yet because I don't have this completely programmed. But you will notice here at the top of our heading indicator, you will see a couple of these little tick marks over here. So you see this little tick mark here and this little tick mark here. What happens is that when you begin to make a turn, you're going to get a magenta line that will emanate here from this, and we call this our lubber line. And this line is going to emanate from this, and it will go in the direction of your turn. If you bring that magenta line all the way to the big tick mark, that is putting you on a standard rate turn. Okay, that's kind of what it is. And the standard rate turn depends on your speed and your bank angle. Okay, in high school I teach you how you can basically know what that bank angle is, but if you have a turn coordinator, all you need to know is I put that wing on that tick mark, I'm going to get a standard rate turn. And in the G1000, if I make this turn and I bank my big tick mark, that's going to be a standard rate turn, which will give me a full turn in 2 minutes. Now, in some cases, you may be required to do maneuvers at what we call a half standard rate. Well, if you're doing a turn at a half standard rate, how long will it take you to make a complete turn at half standard rate? Well, let's see. If a standard rate is 2 minutes and I'm going to be making a turn half that slow again, so that'll be double the time, so that'd be 4 minutes, right? I'll say 4 minutes, Mr. R. Good answer. 4 minutes it'll take you to do that, because in some cases they may need to buy 4 minutes, and it's a quick, easy way for air traffic control to be able to buy time, you know, at your expense, basically. That's kind of the way that works. So this will tell you half standard rate turn here at the little small tick mark. This will be standard rate turn, okay? So that's one of the things that a turn coordinator can do. Now let's look at the inclinometer. The inclinometer, or the shorthand for the inclinometer, happens to be the ball. So if you see here in these examples, you will see that you're making you're banking the aircraft to the right. You are making some kind of a turn, and in this case, you see the ball is deflected outside of these bars. Whenever we want to turn, we want to keep the ball in the center of our inclinometer. That indicates that we are making a coordinated turn. That means that we're keeping the tail behind the nose, okay? We want to make coordinated turns. That's why we have a turn coordinator. So, in this case, what's happening is the aircraft is actually slipping down toward this bank, and we don't want that. So to fix it, you're going to step on the ball. If the ball is deflected off to the right, you're going to use right rudder to move that ball to the center. That right rudder brings the nose around. I'll use Joseph's airplane here. That right rudder in that bank is going to bring that nose around. Okay, it'll push the tail to the left, bring the nose to the right, and that will coordinate our turn so that we're making coordinated turns, so that all of the weight is being pushed down here through the center of the aircraft, and that feeling that you get is just getting squeezed directly into your seat, as opposed to being, you know, off here in a slip, okay? Now, let's look at the other example that we have. This one shows a skidding turn. So what's happening here is that we're actually moving here using Joseph's airplane. We're actually banking here. We're trying to make a turn, but we're kind of skidding out here away from the turn. Well, in order to fix that, you can see here, the ball is deflected off to the left. So we're going to press left rudder. When I press left rudder here, that's going to swing the tail to the right and bring the nose to the left, okay? So that's how we're going to fix that turn. Step on the ball. That will put the ball back in the cage between the two bars, and that's what we want. We want that in straight and level flight. We want that in turns, unless we're doing something different. Like, for instance, in case we're basically making a slip to lose airspeed, and in that case, we're going to do things a little bit different. We're going to ultimately cross-control the airplane. More on that later. So, in this case, if you look at the bottom illustration here, this is showing a coordinated turn. That means that you're turning to the right because you're banked to the right and the ball is in the center. That is a coordinated turn. The big reasons that we want to make coordinated turns: an uncoordinated turn can lead to a stall at a higher airspeed, and that can be a big surprise, especially if you're close to the ground. So we don't want to do that. Now, if we look here at the G1000, how do we do this? Well, guess what this is up here? This is going to be our turn coordinator right here, this big triangle and this bar underneath it. And the way that works is this. In order for us to use that inclinometer, and you see the ball right here and how that ball gets pushed out, this bar will get pushed out here as well. So it's the same principle. If the bar is off here to the right, step on the bar. And that's going to bring your nose around to the right and get your airplane back coordinated. This is an example of your airplane flying wings level and coordinated. Okay? So that's kind of how that works. This is a little bit different. In this illustration, we have these tick marks here to show that our wings are level, right? Well, on the G1000, it's a little bit different. Here we have our little miniature airplane denoted here by this yellow pointer thingy, and you have these yellow bars over here on each side of the yellow pointer, and these are on our artificial horizon line. When we have those wings level on that artificial horizon line, our wings are level. Okay? So that's kind of how that works. Okay? That's the turn coordinator. So when we look at this, that is why we use that. Now we're going to talk about the heading indicator. Or, I'm sorry, not the heading indicator, attitude indicator. Forgive me, the attitude indicator. Goodness. So when we look here, this is an illustration on figure 8-23 of the attitude indicator. You'll notice here that the attitude indicator, it has the spinning gyro there kind of mounted horizontally, and that gimbal, or that little rack that thing sits in, that is what allows that spinning disc to stay on that plane. And when I say that plane, I mean horizontal, and it resists any movement around it. But like it says right there in the book, the basic way that these things work is the fact that that gyro remains fixed and the airplane actually turns around that gyro. As it does, it sends information here by pressure to these mechanical linkages that then give you an indication here on the front of your attitude indicator as to the attitude of your craft. Okay, so that's kind of how that works. Remember, turn coordinator, attitude indicator, and your heading indicator all use a spinning gyro, and they're all mounted differently. If I remember correctly, the attitude indicator is mounted horizontally, the turn coordinator is vertical, and the heading indicator, I believe, is mounted at a 45-degree angle. Much the same way that the actual tubes inside your inner ear are lined up to give you, as a human being, orientation. Remember, am I standing straight? Am I leaning forward? Am I leaning off to the left? Those tubes mounted in that configuration give you that information. Same thing here with the gyro system on your airplane with your attitude indicator, heading indicator, and your turn coordinator. Okay. Now, let's look and see what the presentation looks like here on our attitude indicator. So we have 9 different illustrations here on this figure. The ones on the top row are indicating some form of a climb. The ones in the middle row are indicating level. The ones on the bottom are indicating some form of a descent. And this is figure 8-28. Okay? So before we look at those, I want you to look at this illustration here in the center of this page. Okay? Whoops, I don't want that. Hang on. Darn it. I want this. So let's look here at this illustration. So what we see here is this. We see here that we have the little miniature airplane. That's this guy right there. That is an example of your miniature airplane. This little ball right here indicates that you are on that artificial horizon line separating sky from ground. And that's where you want. You have down here, you have a knob that you can pull that will actually cage this spinning gyro. I'll talk to you more about that in just a second. This adjustment knob right here will adjust your airplane up and down here based on where it needs to be. Once you have that set, you don't need to mess with it very often. And again, this is just using the old style of gyros that we have. Here's your pointer or your lubber line. Remember from the G1000. This is your indicator that gives you your bank indication here. Okay. This is your pitch ladder here. You'll notice that as you get into the blue, 5, 10, 15, 20, okay, those are the degrees up. We have the same thing going down. Then we also have our bank. So for instance, if I'm banking to the right, this little indicator thing will come over here, and it'll begin to kind of look like we're banking to the right. You'll see what that looks like here in just a second. And these are what the hash marks mean. This is 10 degrees, 20 degrees, 30 degrees, 45 degrees, and 60 degrees. It is very, very rare that we would ever bank an airplane 60 degrees, but that's on there. Just know if you do, you're asking the airplane in a level turn to carry twice the weight of that aircraft. So that's what you're asking those wings to do. In most cases, we don't bank beyond 30 degrees. 20 degrees right here at training airspeeds are probably going to be about all that you make those turns, making those standard rate turns. Okay, so that's kind of how that works. A knife edge turn, that's going to be represented by 90 degrees, and that is just so not happening with a training aircraft. So that's what those mean. 10, 20, 30, 45, 60, and 90. Okay, that's kind of how that works. That gives you your bank angle. Right? Now then, let's take a look here at the top line. So if we look at that top line right there, let's look at this. We can see here in this illustration, we can see a climbing left bank. What bank angle is this airplane attempting to bank at? Okay, so remember, that's 0, 10, 20, 30. So he's making a 30-degree bank in a climbing left bank. Notice I didn't say turn, because again, the attitude indicator does not give you turn information, just bank information, right? Here's what it looks like in a straight climb. Now, if we look at this straight climb, we can look here and we can see that we have basically about a 5-degree nose up pitch attitude in a straight climb, okay? If we look over here at this illustration, over here on the right side, you can see that we also have a 30-degree bank for a climbing right bank. Notice how the little dot here, let me get this. I can do this. Well, come on. Well, maybe I can, maybe I can't. Trying. No, come on. There it is. Well, this thing moves opposite the way I always think it's going to move. Notice this. Notice that you have, remember where I said that little airplane symbol thing was going to be right between those two wings? And you'll notice that we're up here in the blue. Remember, the blue is the sky. The brown is New Mexico. Okay? So just keep that straight. Let's look here. Here's what it looks like when you're making a level bank. And again, all of these are going to be at 30 degrees, so no surprise there. So now we notice here that we have our airplane with that nose right there on that artificial horizon line. Same thing here on making the right level bank. Okay? Now if we're descending and we're making descending banks, we expect to have here, we expect to have our nose down somewhere here in New Mexico. In this case, we have about 10 degrees nose down pitch attitude. Okay? That's kind of what we have here. So remember again what the attitude indicator shows us. It shows us our bank and it shows us our pitch. So we can look at bank and pitch on our attitude indicator. Also remember this. By the way, the lights just turned off. Spooky, right? So remember that the attitude indicator is the alpha and the omega. Tell me again what that means. Beginning and end. That is correct. Our scan always begins and ends with the attitude indicator. Attitude indicator, airspeed indicator, attitude indicator, altimeter, attitude indicator, heading indicator, attitude indicator, vertical speed indicator, attitude indicator, what's next? Turn coordinator, okay? That's what we're looking at. And everything begins and ends in kind of that wagon wheel fashion, emanating from and back to the attitude indicator. It's the reason that the attitude indicator here on our G1000 basically is the G1000. That's how important that instrument is. Capiche? Now, we have a couple of different things here. Remember that the heading indicator, turn coordinator, attitude indicator on the old-fashioned instruments all run by something that we call the gyros. What spins those gyros up? It's the vacuum pump. The vacuum pump blows that air on the sides of those spinning discs that over time they spool up. Oh, here's another thing I meant to tell you. When you first turn on an airplane and you start the engine of the airplane, it takes a little while. It takes, in some cases, a few minutes for that spinning gyro to actually spin up to the actual speed necessary to create stability within the case of that particular instrument. So it takes a little while. It's not unusual to start an analog gauge aircraft and have your attitude indicator all, off cockeyed one direction here and being a bit wobbly, just because of the fact that the gyro hasn't had a chance to spool up yet. It takes a few minutes to do this. That will be outlined in your pilot's operating handbook or your AFM, your airplane flying manual, that will tell you, give it 3 to 5 minutes before you can actually make a judgment over whether or not these instruments are operating correctly. Okay, so it takes a while to what we call spool up those gyros. So just keep that in mind. Now then, the attitude, heading, and reference system. We call this AHRS. This is the thing that drives this. All of these electronic instruments are driven by this attitude, heading, and reference system. And what this does is that it picks up basically the lines of flux around the Earth electronically in a solid state fashion without moving parts. We have these things called MEMS, micro electrical mechanical systems. And basically what they are, they're these little button looking things on this little motherboard, if you will, that basically just either sit there and vibrate, or they have inside, they have these little things like little hairs, like you have inside the tubes inside your inner ear. It always fascinates me how much physiology is replicated in the aircraft for movement. So just like the fluid lines inside these tubes, inside your middle ears, those little hairs when they move indicate that you're moving. It's the same thing that kind of happens with these MEMS inside these AHRS systems, and they're called accelerometers. So if you feel like something is accelerating and you're kind of getting pushed back, you will feel that on these little circuits that just kind of sit there and vibrate and detect movement. And so that's what AHRS is all about. So AHRS runs the G1000 system. You can look at that and just kind of read that there as well. The heading indicator, it kind of talks about that here. And again, I don't like the presentation of the way that this works because I almost completely missed the heading indicator. So you can see that the heading indicator, that thing sits at kind of a 45-degree angle, I believe. And you get that gimbal rotation around in a particular direction that tells you kind of where your heading is. Remember on these that in the old-fashioned heading indicators, about every 10 to 15 minutes, you had to take that adjustment knob and adjust that heading to your compass. And you need to do that when you're in level flight, because otherwise we have some compass turning issues that and dip issues that also are at play. So there are times that you don't want to make those adjustments. Straight and level flight is where it's at. So that's kind of how your heading indicator works. Remember your heading indicator, one of 360 degrees, north, south, east, west, and all the different variables in between. Most of you kind of understand how that works. We will get into actual heading stuff once we get to the cross-country stuff and the navigation things here as well. Inside this attitude heading and reference system, this is that box that I was telling you about. This is that box that drives your G1000 or your glass cockpit. Inside are all of those different little mechanisms that feel the movement around that aircraft. And so these things, they are electronic, they're solid state, they're pretty reliable, but they can fail. In fact, I had one fail on me climbing out of Albuquerque, New Mexico, headed to Santa Fe in instrument conditions, and I had an AHRS failure. I lost all of my electronic instruments. When that happens, you go immediately, your eyes get locked onto your backup instruments. It's one of the reasons that we fly the Diamond. In the Cessna 172, your backup instruments are down low near your left knee. In the Diamond, those backup instruments are right center in your avionics panel above your G1000. Your eyes get locked immediately to those instruments. Once I had control of my aircraft and I knew which way was up, I contacted Albuquerque departure. Albuquerque departure, Diamond Star 15 Tree Delta Sierra, declaring an emergency. I've had an AHRS failure. I need vectors to Double Eagle Airport, where I knew they had VFR weather. I got very popular all of a sudden. They cleared airplanes out of my way so that I could get that airplane turned around, standard rate turns, to get headed back toward Double Eagle Airport, land, and get the problem fixed. So you have an AHRS failure, you lose your glass panel, that's an emergency when you are in instrument conditions. If you're in VFR conditions, it may not be an emergency. And the reason being is because you have backup instruments that are going to be helpful. You still got your communications. But again, you want to get someplace, get that thing landed, get it figured out. It's helpful to land at a place that has an avionics shop. Just saying. So that's kind of how that works. AHRS, solid state, very reliable, but it can fail. Just saying. Now, we look at this. This is something here that we call a remote, a flux gate compass. We don't see these much anymore. They are used somehow in what we call a magnetometer. A magnetometer is a type of a thing that actually kind of looks like this, but it's a little bit different. You have that in the right wing of the Diamond, and what that does is that gives you your magnetic information for your aircraft in much the same way that this flux compass used to do on some of the older style stuff. We used to have this thing called an RMI in some aircraft, a remote indicating compass. And in essence what they did is that it kind of fed information to your heading indicator that gave you these lines of flux. Used to be kind of a cool thing to have on an airplane. You hardly see them anymore on the newer aircraft. You know, they've kind of gone the way of the dodo bird, you know, especially with all of the new stuff like this. So this is definitely the new hotness. On the old stuff like this, we would look at these, and this would be kind of how this would work. You would see this on aircraft that came up because these were kind of long-range navigation instruments that you would have here that would sense the magnetic flux around the Earth's atmosphere. And you guys can read those. There are no real test questions on any of the RMIs anymore, just simply because it's kind of an obsolete instrument. You can read that if you want. We're not going to be really kind of too worried about that here for what we're doing here in 8th grade. On your instrument check, remember what I said. How do you tell if your instruments work? Wouldn't it be great if you could tell that if your instruments are working or not before you left the ground? Well, as I say, there are ways we can do that, and we look at that in how the heading indicators, attitude indicators, turn coordinators, and your inclinometers all work when we make turns when we taxi. We're always looking at those things to make sure that things are turning appropriately. Just saying. Now then, angle of attack indicators. These angle of attack indicators, or in some cases what we refer to as a lift reserve indicator, These have been around on military aircraft for a long time, and they are slowly but surely making their way to general aviation aircraft. And what they do is they take in a lot of information on your aircraft, and they kind of give the pilot a visual image of your lift reserve. And when I say that, I'm talking about how close am I getting to a stall speed or to an angle that could produce a stall. And that's what these angle of attack indicators do. There are some that are sort of built into certain systems. There are some that you can add to this. In the Velocity that we're building, we are going to have an angle of attack indicator on the Velocity. And so as we get videos of that, etc., you'll kind of see how all of that stuff comes together. But it is, in essence, gives the pilot in the green, yellow, or red an idea as to, am I pitching up too much? Am I banking too hard? That could ultimately lead me into a stalled condition. That's what an angle of attack indicator is. Gives you lift reserve information. How much extra lift reserve do I have? In the green, I'm good. Yellow, I've got to be cautious. Red, I better be doing it either on purpose, or I need to be either lowering the nose and leveling the wings and fixing that condition before I stall. Stall ultimately, could lead into a spin pretty easy in a real steep turn. So just keep that in mind. Compass systems. So this is the third system. Remember the three systems that we have? Number one, pedostatic. Okay, what instruments? Airspeed, altitude, vertical speed, right? 2, gyroscopic systems. All those things that use gyroscopes. Attitude indicator, heading indicator, turn coordinator, right? The third major category of systems is the magnetic system, or your compass system. And you're thinking, well, now wait a minute. We looked at all this stuff. Here's all this gee whiz stuff here with, all my GPS stuff and some real fancy looking pictures here on this great big screen that I have, which I think even gets ESPN if you tile in the right buttons. Why am I concerned about a compass? What do you do when all that gee whiz stuff turns off? What do you have left? What is that fail-safe instrument that when everything else fails is going to work for you? That's right, your compass. So you need to have an understanding about how the compass works and how it works in coordination with everything else that you do inside your airplane. When we do our navigation information, we boil everything down to the compass, heading. I've had some people here at the door. I apologize. We break everything down to a magnetic course so that we know from magnetically how we get from one place to another. And that's what we still do, so that when all of this stuff shuts off, we can still know how to get our airplane safely to the ground. That's why we do it. So when we look at this, we look at compass systems. And magnetic compass, it's like the oldest, it's the simplest instrument. They've been using compasses on ships sailing around the earth for millennia. And it is still a useful piece of information. But to know how a compass works, we kind of need to know about the magnetic field around the earth. Well, and there is not a good picture here that shows us kind of how that magnetic field works. So I'm going to try to find one here. Stand by. I'm going to try to find one over here on this. So let's go here and let's look at this. So when we look at the U.S., we can see that we have these little lines coming through here. These lines are called isogonic lines. These isogonic lines represent lines of magnetic flux that occur around our Earth. Remember that we have a molten core of our planet. That iron molten core creates a magnetic field around our Earth. And that magnetic field, if you want to think, well, geez, so what? We lose our magnetic field, big deal. What happens? We don't have an atmosphere. So don't be wishing for that one, okay? That magnetic field allows us to have an atmosphere. So we have a north pole up here at the top, a north magnetic pole. We have a south magnetic pole. Here's a question for you. Does north and south, do those magnetic poles, do they ever switch? Yes. Yes, they do. It doesn't happen very often, hundreds of thousands of years. But after a while, remember, that magnetic field moves around. It's not stationary. And over time, if it starts moving too far, it can actually flip. And now south is up and north is down for us here in the northern hemisphere. Kind of kooky, I know, but it does happen here on this planet. There are some scientists that are predicting that we could have a magnetic pole flip in your lifetime. So, just saying. Stay tuned. So when we look here at these lines, the isogonic lines representing the magnetic flux around this, we can actually use those lines to give us an idea of how we need to make adjustments in our magnetic course to fly to some magnetic point. Well, we have to think about this too. We have to think, we talk about, where does a compass point? Well, it points north. North to what? Well, north to the North Pole, right? Which one? That's what I asked. Which one? The North Pole. The magnetic North Pole or the geographic North Pole? Mr. R, are you telling me there are two North Poles? Yep, that's what I'm telling you. There are two North Poles. One is magnetic, one is geographic. I'm getting a phone call. Hang on, this is from one of my favorite students, Mr. William Pryor. William Pryor, say hello to the kids at school. Say hello. Oh, no, he's over here. I'll go on speaker. Say hello to the kids in class.
Hello.
Oh, there he is, that fine English accent. I'll go ahead and take him off speaker. Yes, William. You know what? William, if you will give me, where are you right now? You know what? William, if you can give me 20 minutes. Do you have 20 minutes? Give me 20 minutes and I will call you back and I will meet you at my truck. How does that sound? You're the best ever. You're the best ever. All right, buddy. Thanks, William. Bye. I have some exciting news about William Pryor, by the way. More on that later. So we think about true north or geographic north. That's what we see when we look at lines of longitude or latitude. In fact, let me do this. Let's pull this up, lat and lon, images. Let's look at this. So here we are. Let's pull up this image. So if we look here, we have the lines that go up and down are lines of longitude. Lines that go horizontally are lines of longitude. So if you follow a line of latitude. Lines of latitude are horizontal, longitude are up and down. Okay? Up and down, longitude, side to side, latitude. If you follow one of these lines of longitude from the equator, if you follow it north to its terminus, when you follow that line north, that is when you will get to the North Pole, geographic or true north. I'm trying to find another picture here that I might be able to use to kind of help illustrate this. Stand by. Boy, I'm not finding the one I like. Let's go with this one here. That may be kind of small, or maybe not. Maybe this will work. Yeah, that one works. So if we see here where these lines of longitude all run up here north to true north or the true North Pole, they all meet right here. This is that part that we call, or where they meet, is the geographic North Pole, okay? But that's not where magnetic north is. Magnetic north is over here. Magnetic north is over some lake in kind of northwestern Canada, and it moves. Remember I said that it wobbles around a bit? It's actually moving toward the Soviet Union at about 32 miles a year. This thing moves around. So do you think that when we start talking about here, these lines, these isogonic lines, guess what? These isogonic lines move around. So I'll give you an example. Right now, they are showing this line here, and what we call the isogonic line. Oh my God, I hope I'm showing the right things here. I think I had the screen on the wrong deal, doggone it. Okay, remember, magnetic north is over here. True north is here. True or geographic north is up here. Magnetic north is kind of over here. In fact, that's not really where it is anymore. Right now, it's right over here. And it's over this little bay here in western Canada, up here, moving toward Russia at about 32 miles a year. That's the image that I wanted to be on there. So when that moves around, do you think these move around? The answer is, of course, yes, they do. How often? Well, often enough, because here's what happens. When you look at these isogonic lines, these give us an idea about what kind of an adjustment that we have to make on our magnetic course, depending upon where we are on one of these lines of magnetic flux or these isogonic lines. Only the agonic line, and there's only one of them, the agonic line is the one that if you follow that agonic line, it will take you straight to the North Pole. And it's that line where true north and kind of your magnetic north kind of coincide, but there's no wobbly, with the agonic line. The isogonic lines will all ultimately curve at some point, okay? So when this was published, the agonic line was right here over western Florida. Where do you think that agonic line is now? It's right here. Right here, just over on the west side of New Orleans. So all of these have all moved as well. In fact, 10 degrees east used to run right through Aspen Airport. Now, it's actually a little bit further west, almost over Glenwood Springs. So these move around. This is one of the reasons why when we get the maps out, and we're going to start talking about sectional maps when we get to navigation, it's why those expire every 6 months. One of the big reasons is because of these isogonic lines, magnetic north moving around, lines of flux moving, and having to adjust. I'm going to sneeze. Excuse me. Sorry about that, guys. These lines of magnetic flux moving, or these isogonic lines, we have to repaint them on these maps so that we can make the right correction to give us a magnetic course on cross-country flying. That's why we do it. Now, there are other things that change on those maps. Some of the terrain information, some of the obstacles, etc. Those change as well. But the big reason is because of how magnetic north moves around. Okay? We good with that? We understand. Magnetic north, it's not some static location, and it is not co-located with geographic or true north. Sit somewhere else, okay? So understand that. With this, we all know that a compass, like for instance, if you look at this compass here in figure 8-32, this indicates that we're flying north magnetically. Well, that could be a little bit different compared to true north, depending upon where you happen to be on this planet. So you kind of have to watch that. But that line here, this is our lubber line. Remember me talking about that little pointer? Well, this line is actually the lubber line. So we look here, we have to think, okay, we know we have to make adjustments. We'll talk about those adjustments when we do cross-country flying. But we have magnetic issues that are a little bit different that we have to learn to correct for. So with this, we talk about these lines of variation. When we talk about lines of variation, we are talking about isogonic lines. Isogonic lines on the sectional charts are called lines of variation or magnetic variation. And so that's kind of what we have to do. If you look here, this is another example of what lines of variation or isogonic lines look like here. Now this image is much more up to date. You can see that the 0 or the agonic line is almost right over Lake Pontchartrain, and that is pretty close to where it should be. But now you'll notice how all of these others start to fan out and how they start to flare. Well, we have to account for that when we're flying. One of the trips that I'm going to make this summer in the Dixie Clipper is I'm actually going to be taking that airplane to Alaska. And when I do, I'm going to be having some video about how does flying in Alaska affect the compass, and how does that affect my navigation up there if I'm looking to go from one place to another magnetically. And it's going to blow your mind. So stay tuned for that. So this is how these work. Okay, that's what these lines are, these isogonic lines. So that is magnetic variation. We also have something called magnetic deviation. Variation happens on a map. Deviation happens in the cockpit. And here's what happens. Inside the cockpit, you've got all of these electrical instruments, right? You have stuff in your aircraft that kind of looks like this. Well, do you think that there's a lot of electricity bouncing around inside the cockpit of your airplane? Yep. As that happens, it affects your wet compass, that compass that you have hanging inside your airplane. So when you have inspections, one of the things that the ANP or the AI does on your aircraft is they will actually inspect your compass card to make sure that your airplane compass is pointing in the right direction. And if it's not, they have these little cards that they fill out to say, here's how we have the compass cards, the corrections for your compass. So, for instance, in this particular compass, you have a deal here where you say, okay, 4000, that's north. If your radio is on, you would steer 001. If your radio is off, 002. So you can see that there is a difference whether your radio is on or off. Now, I will also tell you this. Oops, I'm sorry, I had that on the wrong thing. I did that twice. I apologize, guys. This is the compass card inside your aircraft, and it is a card that the mechanic, the ANP, airframe and power plant guy, will put in your airplane. It tells you where to steer based on your magnetic compass, depending upon the electrical instruments in your airplane. So you'll notice here that if your radio is on or your radio is off, you may have actually different headings, magnetic headings that you're going to fly to go here. So for instance, we know that east is 090. Well, if your radio is on, you're actually going to want to put your compass on 095 to actually fly 090. So you're going to add 5 degrees to whatever it is for your magnetic heading above and beyond your magnetic course. So that's what you're going to do. And you're going to learn how to do this when we get to the navigation section of this course. So that is magnetic deviation, and that happens in the cockpit. Okay? So again, remember, true north and magnetic north are not co-located. You also have something else going on here. You have northerly and southerly turning errors. You also have magnetic dip that affects your aircraft. I am not going to hold you to what happens here on this stuff with regard to the magnetic compass, but I will tell you this. If you're on an easterly or westerly heading and you accelerate or decelerate the aircraft, your compass is going to move. So, if you accelerate, your compass is going to dip on the little pin that little compass wheel sits on, and it's going to show a momentary turn to the north. Don't chase it. Do not chase that compass if that's what you're flying on. If you accelerate, it's going to show a turn to the north. If you decelerate, it's going to momentarily show a turn to the south. We use an acronym: accelerate north, decelerate south, ANS. Okay? And that is if you are on an easterly or westerly heading. If you're on a north or south heading, we use another one. And this has to do with turning away from those headings. When you're on a northerly heading, your compass has run home to mama, and it wants to stay there. So if you're on a northerly heading and you turn away from that northerly heading, either left or right, that compass is going to lag behind your turn. It's going to want to stay there. It likes being home with mama. Okay? If you're on a southerly, if you're flying south and you turn away from a southerly heading, again, your compass wants to run home to mama. It's going to want to spin faster than you're actually turning. It will actually lead your turns. So we have another acronym that we use called UNOS, U-N-O-S, undershoot north, overshoot south. That's kind of how that works. Northerly heading, that compass wants to stay there, and it's going to lag behind your turn. On a southerly heading, compass wants to run away from it, and it will actually, the compass will move faster than you're turning. It's momentary. Once you actually get out of that turn and you start leveling off, in just a matter of seconds, your compass is going to be back to normal. But you just need to know that those things happen to your compass, okay? And that has to do with dipping on that pin and upsetting the balance of that compass momentarily while you're making those turns, okay? So that's kind of what happens there. Accelerate north. Compass cards, we're not going to talk about that. Lead and lag, we talked about it. Another instrument inside your airplane that is not associated with those three big categories that we talked about, which is the pedostatic, gyroscopic, and magnetic. You also have other things in your airplane. One of those is an outside air temperature gauge. That outside air temperature gauge tells you at your altitude where you're flying what the outside air temperature is. It will display that information either in Celsius or in Fahrenheit, depending upon how you have your system set up. If we take a look, and I can't do this on this particular illustration, but if you look right over here, you see this thing called OAT, outside air temperature. Right now, it's showing 15 degrees Celsius outside your airplane. 15 degrees Celsius is approximately 60 degrees Fahrenheit. So it gives you an outside air temperature probe. You need that because as the temperatures start going down, you need to know when you are getting into a temperature band that could ultimately lead to airframe icing on your airplane if you flew through a cloud. Understand that that's the only way you're going to get airframe icing on your airplane is by flying through some form of visible moisture. Another word that we use to describe visible moisture is cloud. Okay, so that's what that is. So now, you can see here that we are at the chapter summary. So now, here's what I want you guys to do. I want you to use the balance of the class period right now to begin your review of chapter 8. Because guess what we've got at school on Tuesday? Yes, I know, Martin Luther King Day is on Monday. Tuesday, I think it's the 16th, I think is when that is. I am also administering a final to the high school kids. We should be done by the time you guys get to class. If you get to the door on Tuesday and you see that we have kids in here testing, I want you just to get my attention, just knock gently on the window, whatever that's going to be, and let me know, and then I'll tell you how long it's going to be. I don't expect many, if any, of the high school kids to still be here when you get here. But when you do get here on Tuesday for class, quiz on chapter 8. And I told you the things that you're going to need to know for that quiz on chapter 8. I gave you the bullet points of things that you're going to need to know, as well as how these instruments work. There will be drawings. There will be essay. When I say essay, short answer, okay? And that's what you'll have on Tuesday. Quiz on Tuesday in class. Okay? So, rest of the class today, take this class period, read chapter 8, get ready for the quiz on Tuesday. Guys, Have a great day today, and I will see you on Tuesday. See ya.